Hi there, this is Penelope. This is a short video on the actual understanding behind calculus and why we need it. There's not going to be a lot of rules in here, that'll come from the text and from class, but this is just a basic understanding. It has been said that calculus is algebra with tricks. Don't know about that, but anyway, this video will just give you an overview of basic calculus. Now, we know how to find the area of regular shapes. If this is L by W, we know by formula that A equals L times W. If we've got a triangle, like that, we know that the area is half the base times the height. Even with a circle, we can find approximately the area. We use the formula A equals pi r squared, and then depending on the level of pi that we're using, depends how accurate it is, but it's a formula. The same for finding the volume of something. So if we've got R there and H, then we know that the volume is pi r squared H. And for a cube, or a cuboid, it's x times y times z. So we know all of these when we've got a formula that we can use to find the area or the volume of a shape. But what if the shape isn't regular? What if it's something like that? What if we don't know the rule? So we don't have a formula. Similarly, if we've got something like that and we rotate it around the x-axis, and then we end up with some sort of vase, lampshade sort of thing. Again, there's no formula for finding the volume of that shape. So we need another technique that we can use to find area or volume. Here we've got a curve, and it's a curve that we know the rule for. It's a function y equals x squared. We know what its rule is. Now suppose we want to find the area between 2, which is there, and 5, which is there. So we're trying to find the area underneath the curve in there. So we've got a funny shape. We've got this kind of shape. Well, almost at the top there. Like that. Now, there's no formula that gives us the area of that shape. However, if we know the rule for the function, then we can find the area by using a formula of sorts and some crazy notation. So if the function is x squared, then the area is going to be, and this is just notation at this stage, that's how we find the area. Now, if we know what this tells us to do, we're done. It looks pretty complex, but there's only a few steps. The rule from this stage says we add 1 to the power, so that becomes 3. We divide by the new power, and then we sub in 5, and we sub in 2, and we subtract. So all we have to do is sub in 3, sub in 2, subtract, and we get the answer. Now, in terms of maths, that's not actually very difficult. We just have to follow a rule. Similarly, there's a rule to find the volume. Now, that's kind of half of calculus. The other half of calculus is about finding how steep a curve is, or finding the slope of a curve. If we think of the slope or the gradient of a curve as the rate of change, then you can see how important this could be to an engineer. For example, supposing this graph here is the graph of the population of something against time. So this is the number of units of population. We could easily find the rate of change over time, say from 1 year to 2 years. And if we drew a line like that, then we could use the rise over the run normal thing to find the rate of change. But if we wanted to find the rate of population at 2 years, so there, right at 2 years, for example, then we'd need to find the instantaneous rate of change. Again, if we know a simple rule, then we can do it. The rule for this is to multiply the power of the variable by the coefficient of it and then subtract 1 from the power. So let's say this function is y equals 2x squared plus 2x plus 1. Now the notation for this is either, if this is our function, so if we're using function notation, then the notation for what we're doing here is either f dash, or if we were using the y notation, then it would be dy by dx. So the rule tells us to multiply the coefficient. So we take the power, we multiply the coefficient by it, so 2 2s are 4, and then we subtract 1 from the power. So that would be just to the power of 1, or we don't need to write that. Then the next one, take the power, which is 1, multiply it by the coefficient, that's 2, and then take 1 away from the power, so it would be 0. This is x to the power of 0, so 0 times 1 is 0. Just tidy that up a little bit, that becomes 4x plus 2, since x to the power of 0 is 1. This rule gives us the rate of change anywhere, or in fact everywhere. So if we want to find when x is 2, say, or 2 years, then the rate of change in the population all we have to do is to sub in x equals 2. So when x equals 2, it would be 4 times 2, 8 plus 2 is 10. So the rate of change at 2 years, whatever it is 10 bodies or people or whatever it is to change. Another thing we can use calculus for is to find, for example, the peak or the maximum of a function. Now, if we were to look at the slope here at the top, the slope there is 0. Now we know that the slope we can find by this thing that we just did on the previous slide as the derivative, so that the slope is 0. So if we had the rule for the function, all we would have to do is solve dy by dx, which we can find by the previous rule, for x. And then we're fine. It gets a little bit trickier than that, I agree, but it's only tricky by using the rules. And there's a list. So we don't have to know what to do. We just use a list. So that's the basic thinking behind calculus, both integration, though I didn't use the word, and derivatives.